Stop overpaying at the pump for a problem that takes 5 minutes to fix and costs less than a coffee. Most mechanics will steer you toward expensive tune-up packages, new spark plugs, injector service, throttle body cleaning, when the real culprit sitting right at the mouth of your intake is a fouled mass airflow sensor. We are going to clean this specific component today, reset the fuel trim data in your ECU, and show you the exact moment your engine stops wasting your money. There is a number on your dashboard that is probably lower than it should be, not by a little, by a measurable, calculable, preventable margin. And the cause is not your driving habits, your tire pressure, or the grade of fuel you are using. The cause is a component you have almost certainly never looked at. It costs less than $5 to replace. It is the size of a thumb. And right now, in the vast majority of cars on the road today, it is operating in a degraded state that is costing its owner real money every single time the engine is running. This is the mass airflow sensor. In the world of engine management, this component occupies a position of unusual authority. It sits in the intake tract between the air filter and the throttle body, and its single job is to measure the mass of air entering the engine, with enough precision that the engine control unit, the ECU, can calculate the exact quantity of fuel to inject for a stoichiometrically correct combustion event. Stoichiometric, that is the word that matters here. It means chemically ideal. The precise air-to-fuel ratio at which combustion is complete, efficient, and produces maximum power relative to fuel consumed. For a petrol engine running on modern pump fuel, that ratio is 14.7 parts of air to every 1 part of fuel by mass. Not 14.5, not 15, 14.7. The tolerance that separates efficient combustion from wasteful combustion is narrow. The ECU can only calculate that ratio correctly if the MAF sensor gives it accurate data. The sensor is the primary input. Everything downstream, injector pulse width, ignition timing, fuel pressure modulation, is a calculation built on top of the MAF reading. Now look at these two sensors. On the left, a factory clean unit, the platinum hot wire element exposed and bare, gleaming under the lens. On the right, a sensor pulled from a 75,000-mile daily driver with standard air filter maintenance. The wire is present. The sensor is not physically broken. But that film coating the sensing element, that gray, almost imperceptible layer of accumulated particulate, is the difference between a car that drives the way it was engineered and a car that wastes fuel on every combustion cycle. The MAF sensor does not fail catastrophically. It degrades gradually, and that gradual degradation is exactly what makes it invisible to standard diagnostic routines while it continues to cost money every mile. Here is the polarizing truth about this situation. The automotive service industry is not incentivized to tell you about a $5 fix. A mechanic who identifies a rough, idle, reduced fuel economy and slightly sluggish throttle response will naturally reach for the high-value service items first. Spark plugs, fuel injector cleaning, throttle body service, oxygen sensor replacement. All of these are legitimate maintenance items. But if the root cause is a fouled MAF sensor that costs less than a sandwich to replace, the expensive service items will restore performance only partially because the fundamental data error feeding the ECU has not been addressed. We are going to make that error visible today, with a scanner, with real numbers, and then we are going to eliminate it. Let us get specific about what is actually happening on this wire, because understanding the mechanism is what makes this fix convincing rather than just a YouTube trick. The MF sensor operates on the hot wire anemometry principle. Inside the sensor housing, there is a platinum or platinum alloy filament. In modern sensors, it is typically a film element on a ceramic substrate rather than a freestanding wire, but the operating principle is identical. This element is electrically heated to a precisely controlled temperature above ambient air temperature. As air flows past the element, it carries heat away. The sensor's circuitry continuously measures the electrical power required to maintain the element at its target temperature. More airflow, more heat removed, more power required to compensate. And that power consumption translates directly into a voltage signal that the ECU reads as mass airflow. The critical point here is that the system's accuracy depends entirely on the thermal coupling between the element and the incoming airstream. It reduces the rate at which the airstream can remove heat from the element. The result, the sensor reports lower airflow than is actually entering the engine. The ECU, trusting the sensor implicitly, calculates a fuel injection quantity based on the reduced airflow reading, but the actual air quantity in the cylinder is higher than reported. Inside the cylinder, injectors firing a small amount of fuel into a large amount of air, but the actual air quantity in the cylinder is higher than reported. The injectors fire based on the understated reading, delivering less fuel than the actual air charge requires for stoichiometric combustion. The ECU is not completely blind to this. The downstream oxygen sensors in the exhaust measure whether combustion is running lean or rich. When the MAF underreports and the ECU initially injects too little fuel, running lean, the oxygen sensors register excess oxygen in the exhaust and signal the ECU to add fuel. The ECU responds by increasing what is called long-term fuel trim, a stored correction factor that permanently adds fuel quantity to compensate for what it perceives as a calibration offset. This is what the scanner shows on a car with a fouled MF. Long-term fuel trim value sitting at positive 10, 12, 15%. Not rich enough to cause a misfire. Not rich enough to foul the spark plugs immediately, but rich enough to consume 10 to 15% more fuel per mile than the engine requires. Here is the critical detail that makes this failure mode so insidious. A MF sensor degraded to this degree will often not trigger a check engine light. The ECU's fuel trim correction capability is typically plus or minus 25%, meaning it can compensate fully for the MAF error without ever setting a fault code. No check engine light, no fault code, just a fuel economy number that has drifted downward over thousands of miles so gradually that the driver has simply accepted it as normal aging. No check engine light, no fault code, just a fuel economy number that has drifted downward over thousands of miles so gradually that the driver has simply accepted it as normal aging. The car drives, the ECU adapts, the fuel bill increases, nobody connects the dots. There is one more consequence that compounds over time. The elevated long-term fuel trim is stored in the ECU's adaptive memory. Even after the MAF sensor is cleaned or replaced, the ECU will continue using the old correction factor until it is reset, either by clearing the fuel trim data manually with a scanner or by disconnecting the battery long enough for the adaptive memory to clear. We will address this in the cleaning segment. The millisecond voltage delay that a fouled sensor introduces, the lag between actual airflow change and reported airflow change, also degrades throttle response. The engine's reaction to a sudden acceleration input is governed by how quickly the ECU can see the increased airflow and respond with additional fuel. A sluggish sensor signal means a fraction of a second delay in that response. It is the feeling of the engine taking a moment to wake up. Most drivers attribute it to the transmission or the engine being worn. The real cause is a sensor smaller than your thumb, coated in invisible residue. Brake cleaner, carburetor cleaner, general-purpose electronics contact cleaner, WD-40, compressed air, none of these are acceptable. The sensing element is an extremely fine platinum film on a fragile ceramic substrate. The electrical connections at the base of the element are microscopically thin. Brake and carb cleaners contain chlorinated solvents that will chemically attack the platinum coating. Compressed air alone will drive particulate deeper into the sensor housing without removing it. Brake and carb cleaners contain chlorinated solvents that will chemically attack the platinum coating. Compressed air alone will drive particulate deeper into the sensor housing without removing it. Contact cleaners not specifically formulated for MAF sensors may leave a residue film that creates the same thermal insulation problem you started with. Worth makes an equivalent product that is sold into the professional workshop market. Both use a quick evaporating hydrocarbon base that dissolves organic deposits, oil vapor residue, hydrocarbon buildup, without leaving any residue and without attacking the sensing element material. A can costs between $4 and $8 in 2026. This is the $5 fix. Do not substitute brake cleaner, carb cleaner, or generic electronics spray for dedicated MAF cleaner. The sensing element will be permanently damaged and the sensor will require full replacement, typically $80 to $180 for an OEM unit. The removal process. The MAF sensor on the vast majority of vehicles is secured by either two small Torx screws or a single plastic retaining clip, depending on the manufacturer and model year. Before touching anything, disconnect the negative terminal of the battery, or preferably, use a memory saver to preserve your radio presets and ECU adaptive data temporarily. Locate the sensor in the intake tract. It will be a rectangular or cylindrical housing with an electrical connector and two hose clamp attachments to the intake pipe. Photograph the installation orientation before removal. The sensor has a directional airflow arrow marked on the housing. It must be reinstalled in the same orientation. Disconnect the electrical connector by pressing the retaining tab. Never pull by the wiring harness. Remove the securing screws or release the retaining clip. Slide the sensor out of the intake pipe with a straight pulling motion. Do not rotate or twist. Now examine the sensor element. Hold it under a bright light. The sensing element is the small exposed component visible through the protective cage inside the sensor body. On a clean sensor, you will see a bare metallic or white ceramic substrate. On a fouled sensor, you will see discoloration, gray, brown, or yellowish film on the element surface. The contrast between this $5 cleaning procedure and the service items it replaces is worth stating explicitly. A new set of spark plugs on a 4-cylinder engine, $40 to $80 plus labor. A throttle body cleaning service at a dealer, $60 to $120. A set of new oxygen sensors, $80 to $200 per sensor. None of these address a fouled MAF sensor. If the MAF is the root cause of the fuel economy loss, all of those services will produce partial results at best because the data error feeding the ECU has not been addressed. The cleaning technique is specific and it matters. Hold the sensor with the element facing downward so that displaced contamination falls away from the sensor rather than migrating deeper into the housing. Hold the MAF cleaner can approximately 8 to 10 centimeters from the element, not point blank, which risks mechanical damage from solvent pressure. Apply the cleaner in short, controlled bursts across the element surface. You will see the solvent dissolve and carry away the contamination immediately. The runoff from a heavily fouled sensor will be visibly discolored. Apply 5 to 7 bursts, rotating the sensor slightly between applications to ensure complete coverage of the element circumference. Do not touch the element with any physical object. Do not wipe it. The solvent does the work. Mechanical contact risks scratching or displacing the platinum film. Allow the sensor to air dry completely in a clean, dust-free location for a minimum of 20 minutes. The solvent is fast evaporating, but residual moisture in the sensor housing can cause an erratic signal if the sensor is reinstalled before full evaporation. 20 minutes at ambient temperature is sufficient. Do not use compressed air to accelerate drying. It risks recontaminating the element. While the sensor dries, reconnect your OBD2 scanner and clear the long-term fuel trim data. This step is non-negotiable. The ECU has been storing an additive correction factor, the positive fuel trim offset we identified earlier. That was the correct compensation for the fouled sensor. With a clean sensor reinstalled, that correction is no longer appropriate. If it is not cleared, the ECU will continue to over-inject fuel based on a correction that no longer has a physical basis. You will have a clean sensor being overridden by stale, adaptive data. On most OBD2 scanners, the function is labeled either Clear Fuel Trim, Reset Fuel Trim, or it is included in the Clear Adaptive Data function. On basic code readers that only clear fault codes, the alternative is to disconnect the negative battery terminal for a minimum of 15 minutes, sufficient to clear the ECU's volatile adaptive memory on most platforms. Note that this will also reset radio presets and may require a throttle position relearn procedure on some vehicles. The scanner approach is cleaner. Reinstall the sensor in the correct orientation, airflow arrow pointing toward the throttle body, away from the air filter. Reconnect the electrical connector until the retaining clip clicks positively. Reinstall the securing screws to the specified torque, typically 2 to 3 Newton meters, finger tight plus a quarter turn. The first start is the moment of confirmation. A successfully cleaned MAF sensor will produce an immediate change in idle quality that is perceptible within the first 30 seconds of operation. The idle that had a subtle hunting quality, a slight rise and fall rhythm at 750 to 900 RPM, will stabilize. The engine will settle more quickly and sit at a steady speed with reduced variation. On a fuel-injected engine with a good idle air control system, you will hear the tone of the idle change. Slightly crisper, slightly more mechanical, less approximate. The throttle response change is equally immediate. The first light application of throttle from idle will feel more direct. The hesitation that existed in the dead zone between idle and first throttle response, that moment where you gave input and the car took a beat to process it, will be reduced or eliminated. The engine is now receiving accurate airflow data and responding to it in real time. The real cause is a sensor smaller than your thumb, coated in invisible residue. The ECU requires a short relearning period of approximately 20 to 50 kilometers after the fuel trim reset to establish new baseline correction values. During this period, idle quality and fuel trim values will stabilize progressively. Full adaptation is typically complete within one full drive cycle. Now the numbers. Because feeling the improvement is useful, but quantifying it is what separates a maintenance procedure from a verified fix. At idle with a fouled sensor, a typical 2.0-liter 4-cylinder engine should read approximately 2 to 4 grams per second. After cleaning, the reading at the same idle condition should be within the OEM specification for that engine displacement. For most 2.0-liter applications, that is 3.5 to 5.5 grams per second, a visible upward correction that confirms the sensor is now reading air mass accurately. MAF output at idle, before 2.1, after 4.8. Long-term fuel. Trim, before plus 14%, after plus 1.5%. Idle stability variation. Before plus 55 RPM, after plus 12 RPM. The long-term fuel trim tells the full story. Pre-cleaning, the figure was sitting at positive 12 to 18%, meaning the ECU was adding 12 to 18% more fuel above the base injection calculation on every combustion event. Post-cleaning and ECU relearn, that figure should settle between -2 and +2%, well within the normal operating band of plus or -5% that indicates a healthy, well-calibrated fuel delivery system. The fuel economy translation of that correction is direct and calculable. If your engine was running at positive 15% long-term fuel trim, it was consuming roughly 15% more fuel per combustion cycle than stoichiometry requires. On a vehicle averaging 30 mpg under that condition, the corrected fuel economy after the MAF service should be in the range of 33 to 34.5 mpg, depending on driving conditions, load, and how completely the ECU adapts. In 2026 fuel cost terms, at an average US price of $3.70 per gallon of regular unleaded, a driver covering 13,500 miles per year in a vehicle that improves from 28 mpg to 32 mpg saves approximately $68 per year. That is not a dramatic number in isolation. But it is a permanent saving, achieved for a one-time investment of under $10 in materials and 30 minutes of time. And it compounds. Better air-fuel ratio means more complete combustion, which means less carbon buildup on intake valves and combustion chambers, which extends the service life of components downstream. For EV-adjacent hybrid platforms, including Toyota hybrid systems, Ford PowerBoost, and similar architectures, a fouled MAF sensor disproportionately impacts the combustion engine's contribution to the hybrid drive cycle, reducing generator efficiency and increasing net fuel consumption beyond the pure combustion penalty alone. The preventative maintenance schedule for MAF sensors is straightforward. The primary protection is the air filter. A high-quality OEM specification paper element air filter changed at the manufacturer's recommended interval, typically every 15,000 to 20,000 miles, prevents the vast majority of particulate contamination that reaches the MAF element. Aftermarket oiled performance filters, cone filters, drop-in oiled elements are a specific risk factor. Excess oil from an over-oiled filter element coats the MAF wire in a layer that is chemically resistant to cleaning and will require sensor replacement rather than restoration. If you use an oiled performance filter, inspect the MAF element every 10,000 miles. If you run an OEM paper element replaced on schedule, a MAF inspection and cleaning every 30,000 miles is sufficient preventative maintenance. Here is the homework. The next time you fill up, note your current average fuel economy from the trip computer. Then pull your MAF sensor, clean it using the procedure we have covered, reset your long-term fuel trim, and drive your normal routine for 2 weeks. Check the number again. If your fuel trim was elevated before the service, you will see the difference. Not as a feeling, as a number. Fuel economy does not lie. The service industry has built a business model around the assumption that most drivers will never look inside their own intake tract. $5.30 proves that assumption wrong and keeps the money where it belongs. Drop your before and after fuel trim numbers in the comments. If your scanner showed a fuel trim above 10% before this service, that car was wasting your money daily, and you had no idea. Share this with anyone who has accepted reduced fuel economy as just how their car is now. Like and subscribe for more precision maintenance content in 2026. See you in the next one.